Plunging from a height of dozens of meters, a human life is entrusted entirely to a rope barely 2 fingers thick. Tons of plastic waste are collected and crushed into millions of raw plastic pellets before being melted, extruded into ultrafine filaments, reinforced through a matrix of precision rollers, and intricately twisted and braided into an exceptionally durable structure. A masterpiece engineered to conquer every extreme, from billion-dollar construction projects to critical rescue operations. In today's video, Factron Process takes you inside a modern rope manufacturing plant, where microscopic plastic filaments are transformed into extraordinary mechanical strength. Rope is one of the oldest tools ever created by humankind. Archaeologists have uncovered evidence of twisted cord dating back more than 40,000 years, revealing that even prehistoric people had already learned to combine small fibers into ropes for hunting, hauling, tying, and transporting. Today, rope is no longer just a simple tool. It has evolved into a modern industry, with the global synthetic rope market valued at around $2 billion in 2024, and projected to exceed $3 billion within the next decade. Modern rope has become the backbone of everything from ultra-large ship mooring systems and heavy-duty construction cranes to specialized rescue equipment and high-risk adventure sports. In these extreme environments, rope is far more than a simple means of connection. It is often the final lifeline between survival and disaster. The journey begins on the streets, in residential neighborhoods, and at waste collection sites in cities around the world. Every day, more than 1 million tons of plastic waste are discarded, creating an enormous stream of material that must be processed. Yet there is one alarming reality. As much as 91% of the world's plastic waste is never recycled. Instead, it is buried in landfills, burned, or drifts into the oceans, becoming ghost waste that pollutes the environment and damages marine ecosystems for hundreds of years. To recover the small fraction that remains, this waste stream is collected through various methods, ranging from curbside collection and local drop-off points to commercial recycling services. At collect sites, large garbage trucks equipped with hydraulic lifting systems load their containers with waste before transporting it directly to a materials recovery facility, a recycling center. These facilities can cover between 7,000 and 8,000 square meters and are capable of processing approximately 400 tons of waste per day. When the trucks arrive at the facility, the plastic waste is unloaded into the receiving area. Front-end loaders and industrial conveyor belts immediately begin operating, feeding the mixed waste stream into the processing system inside the plant. From the receiving area, the plastic waste is fed onto an automated sorting conveyor system, stretching approximately 2.5 kilometers in total length. Here, rotating screening drums and powerful air streams separate the material into 5 distinct streams. Next, near-infrared (NIR) sensors identify each piece of plastic in milliseconds before high-speed air jets accurately eject PP, PE, or PT fragments from the mixed waste stream. Alongside the automated line, workers continuously inspect the material and remove any remaining contaminants to ensure the highest possible purity. Once sorted, the PP stream enters an industrial grinding system, where steel blades cut the plastic into small flakes roughly the size of shredded paper. These plastic flakes are then washed several times to remove sand, dirt, oil, adhesives, and surface contaminants. After washing, they pass through an optical color sorting machine that uses 60 high-pressure air nozzles to remove any flakes that do not meet the required standard. After reaching the required level of cleanliness, the plastic flakes are melted and filtered through multiple layers of metal mesh to remove the final traces of contamination before pelletizing. The molten plastic is extruded into thin strands, rapidly cooled in water, and then fed into a high-speed rotary cutter. In an instant, hundreds of sharp blades continuously slice the strands into millions of tiny PP pellets, each about the size of a grain of rice. At this facility alone, the recycling process produces around 20 tons of recycled PP pellets every day, providing a stable raw material supply for the synthetic rope manufacturing process. The next stage begins at the raw material receiving area. Bags of PP plastic pellets are transported by shipping containers to the factory, where forklifts unload each pallet into the warehouse and stack them in neat rows to ensure accurate batch traceability. As soon as they enter the production line, the plastic pellets are fed into a screening tank, a high-frequency vibrating unit that removes all dust and surface impurities. From there, the qualified pellets are transferred to the blending system. Each pellet is evenly mixed with colorants, UV stabilizers, and anti-aging additives, transforming it into a perfectly prepared raw material blend. Next, this material is discharged directly into the steel intermediate hoppers of the central feeding system. Here, the vacuum conveying system is immediately activated, creating powerful negative pressure. Working together with compressed air, it pulls millions of plastic pellets and transports them through enclosed pipelines straight to the storage silos above. From this point on, the raw material officially enters the fiber production line. From the feed hopper, the PP pellets are fed into the extruder, where a rotating screw continuously compresses, heats, and melts them into a uniform polymer melt. The molten plastic is then forced through a spinneret containing hundreds of microscopic holes, producing hundreds of fine filament strands running side by side. As soon as they emerge from the spinneret, the filaments are still extremely soft and prone to deformation. They therefore pass immediately through a cooling water bath, typically maintained at around 68 to 95 degrees Fahrenheit, to rapidly reduce their temperature and lock in both the diameter and shape of each strand. Within just a few seconds, the hundreds of parallel filaments traveling along the production line have solidified, stabilized, and are ready for the stretching stage to increase their strength. After leaving the cooling bath, the filaments pass through a series of drawing rollers, known as godette rollers, where they gain the strength required for rope production. This equipment consists of an array of large metal rollers arranged in parallel and staggered positions. The filaments follow a zigzag path, wrapping around the surface of each roller to maximize friction and maintain precise control. The key principle lies in the difference in roller speeds. The downstream rollers rotate faster than the upstream ones, stretching the filaments at speeds ranging from 400 to 1300 feet per minute. This continuous speed differential elongates the filaments to approximately 4 to 7 times their original length, forcing the polymer molecular chains to align almost perfectly along the fiber axis. As a result, the fibers become stronger, less stretchable, and far more resistant to tensile loads. The entire process must be carefully controlled. If the drawing force is too low, the fibers remain soft and weak. If it is too high, the filaments can snap directly on the production line. For this reason, tension sensors continuously monitor each group of filaments as they travel through the roller system at high speed. Leaving the drawing system, hundreds of parallel filament strands enter the bobbin winding system, where they are collected into large, uniform, and stable packages. Before reaching the winding machine, the filaments pass through a series of metal guides and separator rings that keep each bundle properly aligned, preventing tangles and crossovers. Here, the winding system operates in synchronization with dozens of bobbin stations, winding the filaments at approximately 1,000 feet per minute. Each bobbin is equipped with a traversing guide that moves back and forth across the spool, distributing the filaments evenly from one side to the other instead of piling them in one spot. As a result, the filaments are wound into compact, neatly layered packages. Once a bobbin is full, the machine automatically stops or switches to a new spool, while the completed bobbins are placed on racks and transferred to the next stage. From the freshly wound bobbins, hundreds of filament strands are unwound simultaneously like fine threads converging toward a single point. They pass through separator plates and guide rollers, where each group is kept at the correct spacing and tension to prevent tangling or overlapping before entering the twisting unit. Here, the twisting machine transforms the loose filaments into load-bearing yarns. Each yarn may consist of dozens to hundreds of filaments, depending on the required rope diameter. The spindles typically rotate at 500 to 3000 RPM, continuously twisting the fine strands together. The twist level is critical. For synthetic ropes, the twist pitch typically ranges from 1 to 4 inches per turn, depending on the desired rope diameter and flexibility. If the twist is too loose, the yarns will fray easily and distribute loads poorly. If it is too tight, the yarns become stiff, difficult to bend, and lose flexibility. By the time they leave the machine, the fine individual filaments have been transformed into thicker, stronger yarns with significantly greater load-bearing capacity. Once the load-bearing yarns have been formed, they are fed into a braiding machine to create the finished rope. This is where the individual yarns are locked together through thousands of continuous interweaving motions, producing hundreds of meters of braided rope every hour. On a maypole braiding machine, dozens of carriers holding yarn bobbins travel along preset tracks around the center of the machine. As these carriers exchange positions, the yarns are released, passing over and under each other before crossing around the central core. Some machines have 24, 32, or 48 yarn carriers, depending on the required rope diameter and construction. The core bears most of the tensile load, while the braided outer sheath protects the rope from abrasion, dust, water, and UV rays. As the rope passes through the sizing die, the entire structure is compressed to become rounder, denser, and more uniform in diameter. Each braided strand not only shapes the rope's exterior, but also determines how tensile forces are distributed throughout the entire rope. Once the rope's structure has been stabilized, it enters the stage where it must prove its true strength. First, inspectors check the rope's diameter, roundness, surface finish, and braiding quality using precision gauges or automated sensor systems. Even a single misaligned braid, a broken filament, or an unusually swollen section can become a weak point when the rope is placed under load. Next, sample lengths are cut and tested on a hydraulic tensile testing machine. Both ends of the rope are securely clamped while the machine gradually increases the load to measure elongation and breaking strength. For industrial ropes, these tests can reach several thousand to more than 20,000 pounds force, depending on the rope's diameter and material. Some samples also undergo abrasion testing, saltwater immersion, UV exposure, or repeated bending cycles. This is where the rope is allowed to fail before it is trusted to secure cargo, moor a ship, or save a human life in the real world. After passing inspection, the rope is transferred to the finishing area, where it is cut to the required lengths. Either small coils of a few dozen meters or industrial reels hundreds of meters long. For synthetic ropes, the ends are usually heat sealed to prevent fraying. The heat slightly melts the polymer fibers at the rope ends, causing them to bond together. For ropes used in rescue, climbing, or marine applications, the ends may also be formed into eye-loops and reinforced with industrial stitching before packaging. Next, the rope is fed into a coiling machine or reel winder. The winding shaft rotates continuously, pulling the rope through a guide system so it forms even loops without uneven stacking or unwanted twisting. For standard rope sizes, the winding speed can reach around 30 to 60 meters per minute, fast enough to keep up with the production line while still keeping each coil tight, neat, and cut to the required length. In large-scale factories, automated winding systems can produce several thousand rope coils every day, ensuring a steady supply for both everyday use and industrial applications. A product label is attached to each coil, listing the material, diameter, length, working load, breaking strength, and production batch number. Each coil is then placed on an electronic scale to verify that its weight matches the declared specification. The product is then placed in a plastic bag to protect its surface from dust, moisture, and scratches during transport. For small coils, workers may bag them manually, then apply labels showing the batch code, product code, and inspection details. On larger production lines, the coils are sent onto an automated packaging conveyor, where machines bag them, heat seal the edges, and apply labels automatically. Finally, the products are packed into cardboard boxes, securely sealed with protective tape, and neatly stacked onto pallets. The pallets are then moved into storage, ready for shipment. From here, the rope leaves the production line as a finished product. But the story of rope does not end with modern synthetic fibers. Long before these plastic pellets existed, humans were making rope from an entirely different raw material source. Long before nylon, polyester, and polypropylene, people made rope from natural materials such as hemp, sisal, manila, jute, flax, and coconut fiber. Using coconut fiber as an example, the process begins with the thick husk surrounding the coconut, which contains long, tough fibers. Before the fibers can be extracted, the coconut husks are soaked in ponds or water tanks for several months to soften them. They are then fed into a decorticating machine where steel-toothed rollers crush, tear, and pull the husk apart into long fibers. The loose pith falls away, while the fibers are retained, washed, dried, and combed to remove short strands. Finally, the long fibers are fed into a spinning machine. They are first twisted into thin yarns, then 2 or 3 yarns are combined and twisted together in the opposite direction to produce a stronger, more stable rope that resists unraveling. While synthetic ropes are stronger, lighter, and better suited for heavy loads, coconut fiber rope offers a rough, high-friction surface and is biodegradable, making it a better choice for agriculture, handicrafts, landscaping, decorative applications, and other environmentally friendly products. The journey of making a rope comes to an end here. From raw materials to the finished product, every stage plays an essential role. If you have any questions, let us know in the comments below.